In this lecture slide, we'll talk about inverse trig functions and how to read them. They are very, it's kind of exactly how it sounds. They're inverse values to the typical trig functions. So how it works is that typically, if I said, what was cosine of pi over 6, you would say cosine of pi over 6 is root 3 over 2. Or what's sine of pi over 3? Sine of pi over 3 is also root 3 over 2. The way inverse trig works is that they say arctangent or arcsine, arccosine, like they'll have arc cosine here and then give you the value. And then what you get back like as an answer is the radian or the degree. So instead of saying what's cosine of pi over 6, they'll say what's inverse cosine of root 3 over 2. And then that would be pi over 6 or 11 pi over 6, because this is also root 3 over 2. So typically with these inverse problems, you actually end up having to write down two different answers unless it specifies. So oftentimes, if it's non-specific, you would say, again, in that example, if they're asking what's cosine of root 3 over 2, you would say inverse cosine of root 3 over 2 is pi over 6 and 11 pi over 6. However, if they said within quadrant 1 or within quadrant 4, then that narrows down these two answers to being just 11 pi over 6 or just root 3 over 2. So you have to often be careful if your question is particular about what quadrant or what region your answer lies in. Other than that, then you would have to write down every answer that satisfies this condition. So some examples to hammer this point home. Cosine of 1. Usually you'd say, what's cosine of 0 degrees? And you would say 1. But now if it's asking what's the inverse cosine value when you have 1, the answer is 0 degrees or 0 radians. Similarly, inverse sine of 1 is pi over 2. If it's asking for the inverse sine of negative a half, so I look for all y values that have, oh, that's an x value. See, I already made a mistake. All y values that have a negative 1/2, which there are two, as there should be. There would be 11 pi over 6 and 7 pi over 6. Lastly, if I'm looking for cosine of a value where it's a half, I look for a value where cosine is a half. So here's 1 and here's 1 down here. However, in this number 4 example, they say within 0 to pi over 2. So that means it just wants answers within the first quadrant. Therefore, my answer here is just this radian, which is pi over 3. This example here shows how you would extrapolate theta from something given the angle in the solution. So right here is just kind of like a straightforward example for using the unit circle like we have been, where it's like I have sine theta is equal to a half and I want theta. So I'm asking myself, theta is equal to inverse sine at a half. So sine 1/2 is either this one or this one, which is either 5 pi over 6 or pi over 6. Because again, in this case, we're looking for an angle. But this is an important concept for in all cases when you don't even have a, even when you don't have a radian given by the unit circle. So what I mean is that if you were given anything, like if your answer ended up being cosine theta, and your answer was something like, 22.4 or something like that, in all cases, you can get the actual degree that your function is operating in by just doing inverse cosine on this answer, 22.4. This is obviously something that you plug into your calculator, but the concept right here still remains the same. Whenever you take the inverse trig function of your value, you get back your angle. So that's very useful when you don't understand or don't know your angle in this problem statement. Right here is another good example for solving for theta. I'm tasked to solve for theta, and I'm given 2 cosine inverse of x is equal to 2 pi over 3. So x right here represents our angle theta. So we're really solving for x. To do that, I would start by dividing both sides by 2, which gives me inverse cosine of x is pi over 3. I still want to take the inverse of this thing because I want x on its own. So it's kind of like a nice property. Even if you started on using arc cosine, you can take the inverse of the inverse and still get back the inside value, being whatever it is, whether it's theta, x, or whatever. So I'm going to take the inverse of this thing, of the inverse. The inverse of an inverse is the original because they're like one and the same. It's like saying if I wanted, if I want to cancel out these cosine functions so that I could just get x, and to do that, I would have to have the opposite of whatever it is. So if I have cosine, I'm multiplying it by the inverse. And if I have the inverse, I'm multiplying it by the original, or I'm taking it by the original. It's not really multiplying it either, because I'm kind of like sticking it inside the function rather than like multiplying. Hopefully that makes some sense. So after I take the original of the inverse, I get back the inside thing, which in this case was x, or theta, however they call it. Now I have x is equal to cosine of pi over 3. Pi over 3 is an angle on the unit circle that we could look at. Pi over 3, cosine of pi over 3 is the x value here, which is 1/2. So therefore x is equal to 1/2. So the main key takeaway is that I would say the inverse trig functions are useful when you're not given every piece of information about the triangle, and you're just using a property to get all the pieces of information. So it's like you already know the value here. You already know that cosine inverse of x is pi over 3, but you don't know what x is. So this is just a way to get everything from the triangle.